Welcome back to the 7th video about the Melexis MLX90363 Triaxis magnetometer. In the previous video, we read out all 18 16-bit words from its EEPROM that contained some configuration information, and we decoded that information into proper integer, floats, enums, booleans, and also a single struct. Card here, link in the description. In this video, I want to actually enable our little library to write words to the EEPROM. And believe me, if we at the end are able to write just a single word to the EEPROM, I'll be happy. You'll see. Anyway, enjoy. Just to give you an overview of what the fates have in store for us. So to write to that EEPROM, we need to implement a total of 6 messages, and we will also need the good old knob message, which we already implemented. Card here, link in the description. So MOSIMessages, we have an EEWrite, an EEChallenge answer, and a EERequest. MISOMessages, we need to decode a EEWrite challenge, a EERead answer, and a EERwrite status. The whole process is covered by the datasheet in just a little over 2 pages in chapter 13.17, EEWrite message. That chapter contains descriptions for all the messages, the sequence in which the messages are exchanged between the master and the slave, a table providing you with keys that allow you to write these addresses. There is a different key for each EEPROM address. And finally, a list of possible statuses that you get back with the last MISOMessage. And here's where at least my troubles started. So we saw in that table 21 opcodes. We have an EEWrite, an EERequest, an EEWrite space challenge, an EEChallenge answer, EERead answer. We need the knob and an EEWrite space status. The problem is that, for example, in figure 19, that gives us a sequence, EEWrite challenge is called EEChallenge. Okay, and further down in the different tables describing the single messages, it's called EEWrite EEChallenge. And EEChallenge answer, for example, is named later on EEWrite challenge answer, and so on. I know, maybe I'm just a nitpicker with a very limited mental capacity, but if you read such a flow diagram of the messages and you suddenly come about an EEChallenge, and an EEChallenge was never declared before or after, it was declared before as an EEWrite challenge and declared after as an EEWrite EEChallenge, you just get cross-wired. So instead of looking into the documentation, I will draw out what's supposed to happen. And here's that drawing. So we start out with a SPI transaction sending over a EEWrite message, hexadecimal 3, that contains the address within the EEPROM we want to write to, the data word, that is what we want to write into the EEPROM, and a key. The key you have to look up in a table based on the address you want to write. And as a response in that SPI transaction, we get something. That's not defined, that depends what happened earlier. In the second SPI transaction, we send over to the slave a EERequest message that contains absolutely no data, hexadecimal opcode F. And we get back in that SPI transaction a EERwrite challenge message, hexadecimal 4 that contains a challenge key. That is really the response to our EEWrite from the slave, and this EERechallenge message is only there so we can receive the EEWrite challenge. In the third SPI transaction, we respond to that EEWrite challenge from the slave with a EEChallenge answer, hexadecimal 5, which contains a key echo, which is the challenge key we previously received, XORed with hexadecimal 1, 2, 3, 4, and an inverted echo key. That's the key echo, just binary inverted. And at the same time, we get from the slave a EERead answer, hexadecimal 28, which is just an empty message. In the fourth and last SPI transaction, our master simply sends a NOP message over to the slave, hexadecimal 10. Yeah, we already know that. It contains a key, but it really doesn't matter. What's important is we get in that SPI transaction back from the slave a EEWrite status message, hexadecimal E, which contains a status code that tells us if our whole write operation was successful or not. Of course, we have to meet some timing constraints when we are doing these SPI transactions. So between the first and the second and the third SPI transaction, we have to wait for T short. We saw that constraint before. It's 120 microseconds at 5 volts and 139 microseconds at 3.3 volts. Between the third and the fourth SPI transaction, we have to wait for EEWrite, and that again is written in different styles, all cap or lowercase, in different places in the datasheet, and it's a whopping 32 milliseconds at 5 volts and 37 milliseconds at 3.3 volts. I should also mention that there is an alternative flow of SPI transaction in case we get that key wrong in that EEWrite message. In that case, our EERechallenge gets back directly that EEWrite status message. The flow, in case we got the challenge right, inverting and XORing that challenge key, the flow is exactly the same like if the operation succeeds, so I don't really know why they added that here. After that overview, let's talk about the details now and implement the whole thing. This time I will try to chop up things a little bit more so we don't have at the end, I don't know what it was in the last video, a 10-15 minutes or so code walkthrough. That was a bit harsh. Sorry for that. Anyway, we have 3 new MOSI opcodes, EEWrite, EEChallenge answer and EERechallenge, which we need to put in the related enum, and we also have 3 new MISO opcodes, EEWrite challenge, EERead answer and EEWrite status, which need to go into 2 different enums and 1 array. As you might have noticed, I'm not really fond of the names or different names that have been used for these messages in the datasheet. So I came up with my own. EEWrite will be, of course, EEWrite, and then EERechallenge will be called EERequesting in the enum. ENG at the end because it's an empty message, and we have a second empty message that will also have ENG at the end. We are requesting here a challenge from the slave, and the EEWrite challenge will just be a EEChallenge. And of course, we're sending back a EEResponse to a challenge and not a EEChallenge answer. That's a run-of-the-mill challenge response mechanism, nothing else. EERead answer is, I will call it EEWriting, because here the slave tells us that he's now actually writing to the EEPROM. That's why we have to wait here 32, respectively 37 milliseconds. And EEWriteStatus, I shortened that to just EEStatus, because we can get this message early on if we have the key wrong here, and then it has nothing to do with writing at all. Okay, let's have a look into the code. So, we are in the first private section of my class definition, and I moved that huge command here with the table how the different messages are called in the different chapters of the datasheet here. I also added a column library enum where I documented how I'm calling these messages inside the library. The enum class MISOopcode is the first where we have to do some additions. Our 3 MISOmessages, the EEChallenge, EEStatus and the EEWriting. And you also saw that before the const MISOopcodes array. That was previously at another place. We'll have a look at that in a second, but I also added here our 3 new MISOopcodes. And here's where you saw that array before. In our method valid marker opcode, which I renamed to valid MISOmarker opcode to be more precise. And we don't really need it anymore here because we have it now in the class definition. The reason I put it here into the class definition was, of course, so I can directly check with my enum class MISOopcode if I got all members of that enum class in my array. For the same reason, I moved the enum class received at the start of the public area of my class definition. So I can check directly if everything is complete. And of course, I added here also the EEChallenge, the EEStatus and the EEWriting. In the second private section of my class, I added the MOSIopcodes, of course, to the enum class MOSIopcode. So EEWrite, EEResponse and EERequesting. And that's it for the opcodes. Now let's talk about the EEWrite MOSIMessage. First, we have to supply the 6 least significant bits of the address in the EEPROM, and that address has to be even. I mentioned that in the previous video. Then we have to supply a 16-bit key, which we have to look up in a table based on the address. And then comes the 16-bit data word we want to write into the EEPROM. And the rest is business as usual. Here's the table where we are supposed to look up a key for a certain address. The rows represent the address bits 3, 2 and 1. Remember, bit 0 is always 0 because only even addresses are allowed. And the rows represent the address bits 5 and 4. Pretty unreadable. That's why I scribbled a lot around it. What it comes down to is that the columns really represent the last digit of a hexadecimally written address, so 0 to E. Of course, only even digits here. While the rows represent the second digit of a hexadecimal written address, so 0 to 3. Now, how do we implement all that? We are currently in the private part of my class definition. First of all, we define a new struct address key that contains just an address key pair. Then I define two new constants which were long overdue. That is the number of addresses we know about and the number of addresses we know about that are actually writable. Finally, I define here a constant addresses keys, which is an array of our 18 address key pairs and contains the actual values for the addresses and keys, the read-only addresses being at the very end of the array. Please note that the order of addresses in our array is exactly the same order of addresses we expect in our words array inside our union config. And yes, I'm using that constant addresses here now instead of 18. This all makes our public enum class address, which contains the addresses, a wee bit redundant. Therefore, I changed that enum class address to be just an enumeration 0, 1, 2, 3, and so on of the address key pairs in our array. And of course, the read-only addresses of the MLX ID 15, 16, 17 are also now here at the end. As a consequence, I had to change the implementation of our sendMemoryRead method because it no longer gets here real addresses but just indices into the array of address key pairs. And so here I'm looking up now the addresses within the address keys array. I also had to change the implementation of our config_read method. It previously contained its own array of addresses in the right order for our union config. This is redundant now. We have now that central array in the class definition, and that actually simplifies that method because now we can use here address as just an enumeration between 0 and 17. So yeah, the code here got a little bit simpler. All that's left to do now is extend our private union MOSIMessage with a struct EEWrite that contains the EEPROM address, the key for the address, and the data word we want to write at the correct byte positions. Define a new public method, send EEWrite, which gets as an argument, of course, the address we want to write to and the data word we want to write to that EEPROM address. And finally, to implement that new send EEWrite method, that's business as usual. We initialize here our MOSIMessage local variable with the marker other and the MISO opcode EEWrite. Then we fill within the MOSIMessage union the EEWrite struct with the address, which we look up in our brand new array, and binary AND that with a bit mask so we only get the 6 least significant bits. Then we fill up the key, which we also look up in the array. And finally, we fill the data word with the data word that we got as an argument. And then we do a send MOSIMessage and return the result. That's it. The next MOSIMessage in our sequence, EERequest, at least that's what it's called here in table 40, is really primitive, and I called it EERequesting, that is requesting the challenge from the slave. It's an empty message just containing the marker, the opcode, and the CRC. The implementation is equally primitive. We just define here a public method send EERequesting. and implement it in the CPP file. Yeah, no arguments, so we just initialize our local MOSIMessage with marker other and the opcode EERequesting, send MOSIMessage, return the usual stuff. That's it. What we get back from the slave in the same SPI transaction is the EEWrite EEChallenge, or also known as just the EEChallenge, that contains here in bytes 2 and 3 the 16-bit challenge key and the usual stuff. To implement that MISOMessage, we first extend our typedef union MISOMessage with a struct EEChallenge that contains at the byte positions 2 and 3 our challenge key. Remember, byte positions 0 and 1 were unused. We also need to define a public method last EEChallenge challenge key that returns us that challenge key within the MISOMessage. As you already know, the implementation of such methods in our library framework is quite simple. We just return here the challenge key within the struct EEChallenge that is contained in our last MISOMessage. We're finished. The next MOSIMessage, which we have to send over to our slave, is the, at least here called so in table 42, EEWrite challenge answer. I called it the EEResponse because it's a response to that EEChallenge. And that needs to contain here an echo key in bytes 2 and 3. And the echo key is nothing else than the challenge key we previously received, XORed with hexadecimal 1234. And it also contains an inverted echo key that's just binary inverted the key echo, and then the usual stuff. Now the implementation side of things gets a little bit repetitive. Again, we add to our union MOSIMessage a new struct EEResponse that contains the key echo in bytes 2 and 3 and the inverted key echo in byte 4 and 5, and so they are nicely aligned. We have here unused bytes 0 and 1. We define the next public method send EEResponse, which gets as an argument the 16-bit challenge key we previously received. And here's the implementation of send EEResponse. As always, we initialize our local variable MOSIMessage with the marker other, but this time with the opcode EEResponse. We fill the EEResponse struct within the MOSIMessage. Key echo is set to the challenge key, exclusively ORed with hexadecimal 1234. And inverted key echo is assigned the challenge key, exclusively ORed with hexadecimal 1234, and then a binary NOT of the whole thing. We send our MOSIMessage, return the result, we're done. The MISOMessage we get back in the SPI transaction where we send the EEWrite challenge answer, also known as EEResponse, is just an empty message called EERead answer here in that table. I call it within the code EEWriting because now the chip actually starts to write to the EEPROM. And since it's an empty message, we don't have to implement anything. It was enough to define all the enums for the MISOMessage. At the end of the whole sequence, we send a NOP MOSIMessage over to our slave, and in the same SPI transaction, we will get back a EEWrite MISOMessage from the slave, as it is called in table 44. Within our code, I just call it the EEStatus, and that actually contains, beside the usual stuff, a 4-bit code here in the least significant bits of byte 0. And that code can have 8 values: success, erase, write, fail, EEPROM CRC, erase, write, fail, key invalid, challenge, fail, or odd address. Let's first implement that code as a public enum class EE code, unsigned integer 8. Yeah, it's only a 4-bit code. And I basically modeled that one-to-one as it is described in the datasheet, with one exception I made out of the EEPROM CRC erase, write, fail, just a CRC fail. I mean, they don't use EEPROM in any of the other codes, and the EEReswrite already succeeded, but obviously we got the odd bit wrong when we read back the data. Anyway, I also try to write that out in binary code here to see if I can make sense of the bits, but they really seem to be random. Then we have to add another struct to our private typedef union MISOMessage. And that would be the struct EEStatus, which contains in byte 0 our code. Only in the 4 least significant bits, of course. Because I don't want to rely on the 4 most significant bits in that byte being 0, I introduce a private constant bitmask code with just the 4 least significant bits set. The last thing we need to add to our class definition is a public method, last EEStatus code, which returns us that code. And here's the implementation of that method in the CPP file. So we take that EEStatus struct within our last received MISOMessage, we take that code byte within the struct, we binary end that with a bitmask for the code, cast it to an EE code enum, and return it. Now that we've implemented all required messages to write to the EEPROM, we can create a high-level function within our library that implements the whole process. Remember, it takes a total of 4 SPI transactions to write a single word to the EEPROM, and we don't want to burden our application with that. That should be done by our library. Just to recap, we already talked about that in the overview. We first send a EEWrite message to our slave and we get something back. But we don't really care what that is. Besides, that's really determined by what message we sent before to the slave. Next, we send a EERequesting message to our slave and we get back an EEChallenge message. In the third transaction, we send over the EEResponse message to that challenge to the slave and we get back a EEWriting. Then we wait quite long because now the EEPROM is actually written to. And finally, we send over a NOP message to the slave and we get back our EEStatus message. That was the normal flow of messages, where we get back with the EEStatus message from the slave at the end, a success. However, we can also get at the end some error codes, of course. And if we provide an erroneous key, or, that's my interpretation, an odd address in our first message, the slave will not answer to our requesting of a challenge with a challenge, but directly with an EEStatus, containing the error codes for an erroneous key or an odd address. Why they don't mention the odd address here in the datasheet, I don't know. And And here is the public method declaration within our .h file. So I called that eepromWrite, and it gets as an argument the address we want to write in the EEPROM and the 16-bit word we want to write. I also extended the public enum class library error with some errors we might encounter in that method. So yeah, wrong key, wrong address, EERequest failed, CRC error, and the challenge failed. The implementation of that method in the CPP file is necessarily a little bit lengthy. We start out by sending a EEWrite message to our slave with the address we want to write and the word we want to write, and if that fails, we return false. We wait the appropriate time. I choose here the 3.3 volt value to be on the safe side. And then we send next that EERequesting message. And if that fails, we also return false. Then we check if the last received message from the slave was actually an EEStatus message, meaning we did something wrong here with the address, or inside EEWrite something went wrong with the key. So we switch here over the last EEStatus code, and if that's key invalid, we set our library error to EEKey. Respectively, if we get odd address, we set the library error to EEAddress and return false, of course. Next, we check if the last received message was indeed a EEChallenge. We don't expect anything else here, and if we get something else here, something is wrong, and we set our library error to opcode and return false. Otherwise, we wait again for the usual time, t short, and then we send our EEResponse to that received EEChallenge challenge key. If that fails, of course, we return false. Then we check if the last received message we got back to that was EEWriting. If that's not the case, again, library error opcode, return false. And then we wait for a full 37 milliseconds. That's the value for 3.3 volt operation, playing it safe here again. Finally, we can send our last message to the slave, a knob. If that fails, of course, we return false again. And we check if we get indeed a EEStatus message back from the slave to our knob message. If that's not the case, last library error opcode again and return false. At the very end, we check if our last EEStatus code, which we got with that EEStatus message, is indeed EECode success. If that's not the case, we switch over that last EEStatus code and we set our last library error according to the EE failure code we got. So EERequest fail will become an EERequest, CRC fail will become an EECRC, and challenge fail will become a library error EEChallenge. And we return false. Otherwise, everything went smoothly and we return true. Now we can use that library method to actually write something to the EEPROM. So in the setup, I made some additions. So that part is still the same old. We do a begin, we do a config read, and then I check if the config user ID is actually 0034567. Remember, the default is 003001. If that's the case, I print out here EEPROM already written and I return. That is, I leave the setup. Otherwise, I'm printing here writing to EEPROM and I call that EEPRomWrite with the address user ID 0 and try to write into that 16-bit word that 4567. If that fails, I call my handle MLX last library arrow function here, which I also extended. So, handle MLX90363 last library arrow now also prints out our new library arrows EEKey, address, EERasWrite, CLC and challenge. The loop is unchanged, just printing out the configuration every second. And here's how the whole thing looks on the serial monitor after I tested the code. So we get here the printout in our setup EEPROM already written, and indeed the user ID here is now 34567. That's a portion we've written just to the EEPROM. But that's not really what I wanted to show you. Let me close the serial monitor and see if we can do a little bit better. And I'm comparing now here to FFFF. And I'm writing here now FFFF. Let's upload the whole thing and start the serial monitor again. Okay, serial monitor. Let's stop that and go to the top. Oh, yeah, opcode error. I don't know where that came from. That's from in our begin procedure. Yeah, still room for improvement, but it EEPROM already written. So after upload, the code executed and was writing to the EEPROM already. So we would expect now a user ID of, yeah, that is 3FFF. It works, but yeah, between uploading, the upload finishes, the thing starts executing its script, and me starting the serial monitor, and the thing actually printing out then on the serial monitor, it already writes to the EEPROM. Yeah, nothing I can do about that, but it works. That's it for today. We've successfully written a word to the EEPROM. But that's of course only the start. Next time we do exactly the same for writing parameters to the configuration.